I think you can all see the screen, and on the screen you can see our book. We were discussing space-time codes, the famous LMOT scheme. Can you all
book
see?
share नहीं हो रही अभी.
Book is not shared, so I will try
सर
again.
आ गई है, आ गई है.
All right. So in the last lecture, we were able to drive the famous, very important equations of LMOT scheme, and this was the proof was shown. So, and you could see that the gain was again two diversity gain was available because you have H mod, which is now H1 H2. Now we will be comparing this scheme with other schemes. So first of all, we try to compare this with the repetition code. So you can see that what is happening here in LMOT scheme is that you are sending two symbols over two symbol times. But you were also sending two symbols compared to repetition code. There you were sending actually one symbol in two symbol times. Remember repetition code? You send one symbol, then in the next symbol time you have to repeat the same symbol. But what is happening in LMOT that because of antenna diversity or because of spatial diversity, you can send two symbols at one time, then you can repeat those two symbols in another time. So in order to understand it, I've just written here that if we assume that transmit power is same in both the cases, that is in LMOT and repetition. So you can see repetition is sending two symbols in two time. In other words, this is 2 divided by 2, it is sending actually one symbol per time. But repetition is sending one symbol in two times because it has to repeat the whole symbol in the next time slot. So it is sending only 0.5 symbols per symbol time. So if you assume that power is same, then you can see that LMOT rate is greater because it is sending one symbol in one time as compared to please mute off your microphone. If you have any question, then you can unmute and ask. Now this is first thing. Now second thing you can see. Yeah, please unmute yourself. All right. The second thing that we can notice yes, but with half the power in each symbols. So you are sending two symbols, but with half the power in each symbol. If I assume that the total power is same, so that was the same thing I was showing you here, that you have two symbol energy is equal to one symbol energy of PAM. So in that case, you can see that one energy of LMOT is actually half energy of repetition. All right. If we assume that the symbol energies are same. So in the second case, let us say that these two symbols on which LMOT works, let us say they are BPSK symbols. All right. So you know BPSK symbol is minus A plus A. So only two symbols, you just require one bit for representation. So if you are sending two symbols, you just require 2 bits. So it is sending actually, if I use BPSK or LMOT, it will be using 2 bits over 2 symbol times. Now, if I compare this with repetition, okay, and if I want to keep the data rate same, so I want that both the schemes, PAM over repetition or BPSK or LMOT, they must have the same data rate. So I must use 4PAM because you know 4PAM has actually 4 symbols. If you remember, minus 3b, minus b, plus 3b. So 4 symbols will require 2 bits. All right. So, and it has a repetition code, so it repeats once, it sends once and then repeats in the next slot and other coherence time slot. So once it repeats, so it is repeating those 2 bits again. All right. So actually it is sending 4 bits in 2 time slots, or in other words, it is sending 2 times, it is sending 4 bits, the 2 bits in 2 time slots. So it is sending actually 1 bit in 1 time slot, as was the case of LMOT in BPSK. So this I have shown here. You can see here. LMOT is sending BPSK, which is sending 2 bits in 2 symbol times. So it actually is sending 1 bit per symbol time. If I want the same rate of repetition, I will use 4PAM. 4PAM is using 2 bits and repeats 2 bits in 2 symbol times. It is using 2 bits in 2 symbol times. Overall, it is sending actually 1 bit in 1 symbol time. So now I have kept the rate same. Rate same. Okay. So once I kept the rate same, then I will compare other things, power or minimum distance. Coming back to the book. Now, if I say that I want to achieve the same minimum distance as the BPSK symbols in the LMOT scheme, same data rate, then, and for same distance, what will be the requirement in terms of energy per symbol? So that can be seen here. I found that it is not explained properly in the book in terms of mathematics. Now please see, please ignore this part. Now repetition with 4PAM, what is the error? Same thing. We just solved it previously. Any repetition scheme, its error is given as 2H mod S and LMOT with BPSK we found it is also the same. All right. So it is the same 2H square SNR, both has been shown previously. But what is the difference? In 4PAM, we know that SNR is 5B square over N naught, but in BPSK it is A square over N naught. Now what is the meaning of same minimum distance? So, you know, same minimum distance is actually that the distance, what was the distance in BPSK? If you remember, in BPSK, you had minus A plus A, distance was 2A. And minimum distance in PAM, you know, it was either between minus 3B minus B, or between minus B and plus B, or between plus B and 3B, which was again 2B. So if I want to have the same distance, I must have these two equivalent. I must have B is equal to A. Now if I say B is equal to A, then in this case this will become B square. Now you can see, in order to keep the same minimum distance, I am requiring 5B square SNR, or signal power 5B square as compared to B square. So it requires 5 times more energy per symbol as compared to LMOT scheme. This was the meaning of this sentence. Say it needs 5 times the energy per symbol. Now, taking into account the factor of 2 energy saving, since we are only transmitting 1 symbol at a time in the repetition scheme. Yes. Now, but in repetition, we know, and we have just seen that what happened, that it is sending only 1 symbol at a time. It is not sending 2 symbols at a time. So you can see that in repetition 4, you required 5 cross 1 symbol energy of BPSK, while in LMOT scheme it is requiring 2 cross 1 symbol energy of BPSK, because it is actually sending 2 BPSK. We cannot, in the last slide I was comparing their energies, but you know it is not that equivalent in a way, because we are sending 2 BPSK. We are not sending 1 BPSK symbol. We are actually 2 sending BPSK symbols in the LMOT scheme. So now we compare 2 with 5. If we take the ratio of the energies, again you can see, all right, not 5 times, but it's still 2.5 times greater or more energy as compared to BPSK of LMOT is required to maintain the same minimum distance. Same minimum distance means same bit error. All right. This is what is he's saying. Now, what is the analysis? Why this is happening? Why LMOT is giving a better rate if you keep the power same, and if you keep the minimum distance, and if you keep the rate same, then you can see it is requiring less energy. Why it is happening? What is the analysis? This is the analysis that in BPSK you can see all the bits they are along only one signal direction, H1, H2. But in LMOT, you could see that you had information along two orthogonal dimensions. One was H1, H2, and the other was this, and they were both orthogonal. This is the reason. Next, he tries to discuss the determinant criterion for space-time code design. So again, we can discuss this purely mathematical, but it gives us a lot of insight and it is very important discussion. So. Before, I would like to do one thing, and the problem with starting and understanding space-time code design requires one further step, and that step, as you can see here, that in the LMOT scheme, your data symbols might be complex. Till this point, we have studied repetition, all right, or we have studied rotational coding, but you could see that in all those schemes, we were assuming that our symbols, they were all on the real axis or I channel. None was on the Q channel. Even for the rotational codes, when we were saying discussing, so we said that they are of BPSK, so all of them were AA. None of them was on the Q channel. Okay? But here you can see there is a difference. The first difference here comes that LMOT utilizes the Q channel because it is conjugate. Conjugate means that if, let us say, it has an imaginary part, this will become minus j. So you can use BPSK, so in that case, it will be still on the real space. But if I use, let's say, QPSK or other schemes which also utilize the Q channel, then you will be working on both the I and Q channels. So we have to define some formula for defining the error in a vector space, but the vector is complex. Till this point, we have defined the error in vector space, but that vector space was not complex, it was real. So before we go on, we should discuss, because it's a very, very important discussion, and if I miss that, then most of the students will not be understanding about other things. Now, if you could remember, going back to this very important appendix, so we have done all of that appendix. So we had done this proof that error actually depends on if UA and UB a vector and UA and UB are in the real space. So the error probability in confusing UA with UB is given as follows. This was proven very clearly. Now we want also to go to the proof that what happens if the vectors are in complex vector space. Now before we do this proof, he has actually tried to proof on an alternative view. Okay. So I will try to discuss this alternative view. Okay. And let us try to understand, because this view is very important in our subsequent discussions. So again, we say that at this point we are still talking about real space. Okay. But the proof that we have done previously was pure mathematical proof. We did one single step and we were able to reach the conclusion. Here we will be trying to use intuition and directly jump to the previous results by using, but these intuitions carry a lot of weight. Again, we are saying we have two vectors and these vectors are in real space. All right, U and UB. So we have to again find the probability of error in the confusion that we are either detecting UA or UB in the real space. So let us say we transmit vector U Generally, we try to represent it as follows, and you can say that u is equal to this thing. So it is general expression. If I put x is equal to plus half, then you can say that UA will add and this will give you UA. This will be minus half cancelled with plus half, and UB will be cancelled. So by just giving x different values of plus half and minus half, I can say that U will be equal to either UA or it will be equal to UB. So it is just another way of writing that U is equal to UA or UB depending on the value of x. Now, this is a transmit vector. So this transmit vector will be received at the receiver. Receiver will be actually equal to U plus W. Okay, U plus W. So I take this on the other side. Your Y will be equal to U plus W. I take this on the other side. This will become Y minus this is equal to this remaining plus the noise. Again, no change, just shuffling of equations at this point. Then we will discuss afterwards. Now here is a very important point. We try to define a vector, okay, and you can say it as a unit vector. In other words, you can say, but this unit vector is actually in the direction of UA minus UB. Right. So I say this is a vector V normalized. In other words, so this is the vector. I divide that by its energy mod square, mod. Okay. In this way, this will be a normalized vector, okay. And now the components of the receive vector. So actually, the proper words would be the components of the receive vector y minus half UA plus UB. They are actually equal to sum of these two. So, so you can correct this, and that the components of the receive vector y minus half, okay, are in the directions orthogonal to V, contain purely noise. So you can see here that if this is the receive vector, okay, and whole of this is now along UA minus UB. This is a value, but you can see it is along this V vector because we have taken the direction of this. In all other directions, you have actually noise. Noise also present in this V direction, okay, but all other directions will only have noise. Okay. So receiver in direction orthogonal to V contain purely noise. Okay. Due to the isotropic property of W, the noise in the direction is also independent of the noise in the signal direction, because W is actually a vector. All right. It is a noise, the received noise in all the values of Y vector. All right, which is 0 and not by 2 if it is only working in the real space, and they all are independent of one another. So this shows us that the components of the receive vector in these directions are irrelevant for detection because the whole signal is present only in the V direction. Rest of the directions, okay, they are not containing the signal because signal is only present in V. All other are not important. So what we can say that we just project the receive signal. This is a receive signal. We just project our receive signal onto this direction V, okay, and do our detection on with respect to this variable, because if this is a vector and this is a vector and I project one vector onto another, so from the dot vector I will get a scalar value. So I just base my detection on this number, on this Y. All right. Once I do that, you can very well see that actually I have converted my problem from a vector detection to a scalar detection problem. So this figure is 8.6 here. Here you can see that this is UA, this is UB, and let us assume that UA minus UB, Yes, this figure is more better. This is UA UB, and this is a vector UA minus UB. All right. So if you remember in electromagnetics, we had na the R1 position vector, R2 position vector. All right. So what is this? If this, let us say R1 position is R2. So what is this position vector? So if I say this is R1 and let us say this is R2, then we know that R1 plus R is equal to R2 position vector. So in other words, R position vector is equal to R2 minus R1. So in other words, this vector is actually equal to UB minus UA. All right. So we are projecting Y onto this line. All right. So here he has taken UA minus UB. So this will be actually a vector going from UB to UA. So we are just projecting this Y onto this vector. All right. This is what we are doing here. So we can say that we are actually viewing the receive vector. Okay, this is a receive vector in different orthonormal basis. Acha, I will take one moment of break to let us see that. Oh, some student is waiting to be admitted. Please, you can admit yourself. All right. I just wanted to ask one question here. Do you remember this orthonormal? Because you can see here is saying the yes, we are viewing the differential vector in different orthonormal bases. Does anyone remember what is different orthonormal basis? Do you remember what are orthonormal signals? Does anyone know what are orthonormal signals? I think you those students who would have studied digital communication, they would know. So what are orthonormal signals? Actually, orthonormal signals are a set of signals who are orthogonal to one another and their energy is actually normalized. So if you see here, these are orthonormal signals. For example, I have this signal, all right, and if I take their dot product, this is the dot product, just multiply them, and if this comes out to be 0, this means x1 and x2 are orthogonal, and if their energy actually energy is this thing which is square under root, because you know square becomes power and then I take integration over whole time, so power, this will become energy. So their under root of the energy, this ex is energy, and their energy is 1. If energy is 1, so their norms, this is called the norm. So if their energy is 1 and they are orthogonal to one another, then they are called orthonormal. All right. This is so you can let us say you have a set of signals, you can form their orthonormal basis. This is you can form their orthonormal basis. A lot of is given in digital communication how to find their orthonormal basis. These are very famous Gram Sandwich procedure. So you know these. So you have these signals. So I form orthonormal basis here for this and this and this, and I can write these signals in terms of their orthonormal signals. Okay. So we won't go into detail to let us do lengthy, but just to tell you that you might have so you have, let us say so this is S4 actually. So you might have many signals, it is S4 signals, but your orthonormal basis, they just come out to be 3. So all of the above signals can be represented in terms of these 3 signals. Okay, so this is the dimensionality of your signals, right? Orthonormal basis. So this is just to repeat that what is the orthonormal basis. So first direction is given by V, other directions are orthogonal to each other and to the first one. Okay? So in other words, what we can say that if I use an orthogonal matrix, where in this matrix I can say that the first row is V. Okay? All other rows, okay, they are actually other orthogonal directions which are not only orthogonal to V but are orthogonal to one another. All right, so they are all orthonormal bases. All right, so I use them. All right, and I do my I multiply that orthonormal orthogonal matrix having orthonormal basis multiply with output. So this will be multiplied with input. Again, you know the book misses certain steps, so I have done this here. So just for explanation, so I have this vector which is V and all other rows which are orthogonal to V and one another. So I multiply this. So you know this output is equal to this thing. So I have multiplied my matrix with this with this. So now this V will go with this XUAV. So what is V? You can see that V is actually UA minus UB over U. This V we have just found. It was actually this thing. So it is as in a form of a row. So I will write its transpose. So once you do its multiplication, you can see this will become transpose for real. This will become UA mod square, and this is mod. So this cancels. So just X into UAB. But all other matrices, they are actually orthogonal to this. So they will give you 0. Right, because orthogonal they will, so not written, but you can just see they will be all 0. Now when this will go with W, so you know this is n cross n, and this is your n cross 1. So you get an n cross 1 matrix, but you can see that W is a Gaussian vector. This is a orthogonal transformation, so it won't change. The result will not change. Okay. So this has actually been discussed. If you could remember here, we had seen here that if you have a Gaussian vector, so it is invariant with respect to rotation. Yes. So if W is a standard Gaussian, in this case it is 0 and not by 2, all the values are 0 and by 2. Then OW, where O is an orthogonal transformation. Okay. So where O, we said it has all these orthogonal vectors. Then OW is also standard Gaussian. Okay. So this means that this will be also a vector, but all will be standard Gaussian. Okay. And rest of them, this you can put 0 0 here, or there will be 0 0. So this will come out to be like this. So, but all these 0 zeros and all these NNs, this is actually for a vector. I, this represents a matrix, so it is a covariance matrix. This is a vector representing a vector. So, but rest of the bases are not important. We are just concerned with the first basis, which is important. So we just want its statistic. All right. So here also we have a matrix, but we just want the first one where V is multiplied with this. So we just take out that first entry in our rows, in our these column matrices. The first entry will be Vt into this vector. Okay, all others are not important. Then I take this first entry from here. Its first entry will be W0 and not by 2. This will be a scalar. So you can see that our receive static okay, will be actually again x into UA minus UB plus W. Now we have done a huge transformation. Remember, UA is a vector, UB is a vector, but UA minus UB mod, this is a scalar. I've converted a full-fledged matrix, a detection problem or a vector detection problem into a simple scalar problem. All right. So we just have scalar times x w, okay, and that x was half or minus half. So we have actually two symbols. One could be plus, another could be minus, and the distance between this plus would be like this. So you have now a problem, okay, where you have two scalar symbols. One is present here, one is present here, and the distance between this. So what is a singular noise? What is a noise ratio? Use the previous scalar problem, where you know the problem was that between two scalar, the probability of error was just the distance between them, and the distance between these two scalars is this minus this, which is actually this. So this is the error. So this is a intuition. Based on intuition, you have just developed a solution which is actually proving our previous result. So you can see that our previous result, which we did with full-fledged mathematics, was also this tape on the result. And this, which we have done with intuition, it is also giving us the same result. Okay. But in making this result, we have seen various. We have seen that we have developed very good tools, and one tool is that yes, this y scalar is sufficient. We don't need other bases. All right, and you just have to project the received y onto the v vector. You will get that y tilde. All right. So y tilde is just projection of received onto v. So this is a sufficient projection, and this operation is called match filter. All right. Yes, it only depends on the distance on the between them, and yes, all that. Now, based on this, now we can develop our projection in vector space, in a complex vector space. No problem. Now again, we have this problem where u could be ua, ub same, but ua, ub are now complex, and w becomes a complex Gaussian noise, but a vector, a complex vector Gaussian noise plus I. Again, I say you can be represented like this, where x is equal to plus half minus half, and I can get ua, ub. Again, I form my v vector as previously, knowing that this is complex, no problem, but same. Okay. Now again, I develop the same projection. Okay, projection of the receive onto v as it is previously, but only difference because there they were all real, but there it is a complex vector. So I have to say VH or V Hermitian, which the book writes as V conjugate, which means transpose plus complex. Okay. And you can see you will be getting this thing again, same thing you will be getting. Okay, and you can do the mathematics yourself. But W will not be simple N naught, it will be C N naught, because it will be a complex random variable. Okay, the statistic is there. We just take the sufficient statistics. The first part, all other are not important. So I can develop my again I have transformed my space onto a real space, but onto a scalar space, but I can say the scalar space is actually real plus imaginary, because it has a real and imaginary part. But if I take the real on both the sides, now this becomes totally real, and I know its error is again q into ua minus ub 2 under root n naught by 2. All right. Similarly, I can form the imaginary, which will be again the same value. So if I combine error on both the sides, real and imaginary, assuming that the error is equally probable, I will get the total error is as this value, same as I was getting in the real space. So you can write it yourself. It is not that difficult. You can do yourself, not a problem. The total error will be half plus error, half into error in the I phase plus half into error in the Q phase. Now error in the I and Q phase is this thing. Half plus half of this will give you total Q. Total error will remain the same as in the previous cases, but the only difference is that U and UB are complex. Okay, but again, once you will be taking their negative and mod, so everything will come out to be a simple number, scalar number, and you can just find the error. So this was the derivation of a very important result, that error is just dependent on the difference of the received symbols. This is the total result for any domain. Okay. Now coming back to our lecture. Oh yes, first of all. Now we try to develop the criteria for space-time code design, as we develop the criteria for time diversity codes. So here we try to develop for space-time, not only time but space-time. So first of all, he says that how can I develop a code word? That is very, very important. Okay. Remember, when we were developing a code word, for example, convolution code or linear block codes or our rotational codes. So if you could see, those codes, okay, one were only time, but you could repeat them through space, as in the case of rotational code or repetition code, you were repeating your set of symbols. Here, if you would see that we have to develop a code both in space and time. All right. So the size of our code will be L cross N, where L will be the number of antennas and N will be the length of the code. For example, in LMUT scheme, you could see we were using 2 antennas. So, a number of antennas goes as rows, and the number of time slots they go as column. So its size will be 2 cross 2. But you could have codes, for example, yes, you are using 2 antennas, but let us say their size is they have 8 diversity or 10 diversity, so their size will be 2 cross 10. So in LMUT scheme, our code word will be of this size, because first symbol goes as second, then the second conjugate is sent from the first antenna, and U1 conjugate is sent from the second antenna in the second symbol time. All right, where we assume that the first the channel remains the same in the first and the second symbol time, channel remains the same, but these two H1 H2 they are uncorrelated or fade independently. So for example, what is the code in repetition scheme? So in repetition scheme, I will send one symbol through one antenna. Okay, then you know that in the second symbol time I will send the same symbol but through another antenna. All right, so those two symbols will be reaching through two different channels. All right, so I will not be sending the same symbol through the second antenna, that is it is 0, and sending the same symbol to the first antenna. So I have to keep other silent and only one has to send. This is the repetition scheme. So its code word will be given as follows. So if I have any block length L time diversity code, for example, rotational code or convolution code or all other codes, linear block codes with code words xi. So you have code words xi. For example, in rotation you had code words AA minus AA minus A minus A. So it will translate into a block length L transmit diversity code with code word L cross N. L transmit diversity code with code word matrices. They will be diagonal, as repetition scheme, so it will be diagonal. So all the code words, okay, they will be placed like this: first year, second year, third year, fourth, because you are using repetition scheme. They will be placed along the diagonal. So first symbol will be sent here. Then if you want to repeat it to the second antenna, it will be sent here. It will depend on the length of the code that you choose. If it is say 2, then it will be 2. But if it's 3, 4, you have to send it whatever the length you have chosen. 4 times or 5 times repeated or 6 times repeated. For example, in rotational codes, you are repeating 2 times. So we are normalizing the code words so that the average energy per symbol time is 1. Again, a square over n naught, or whatever the energy, that is kept 1. So SNR is equal to not a square over n naught or b square 5b. This is just 1 over n naught. And assuming the channel remains constant for n symbol times, we can write our received signal as follows. All right. So just for making it more clear, just written this equation that we will understand here. So now you will be getting n different outputs because you are using n different time slot, because your code symbol has L antennas, 1, 2, let us say L, but these L antennas, they have n slots, as in Malamuti you had 2 cross 2. Right? So you will be getting outputs with respect to time slots you are occupying. So you are occupying n, you will be getting n outputs. Okay. Channel coefficients, they will correspond to number of antennas. So you have L antennas, so this will be H1 into HL. So you will be assuming that for space time, we have assumed that these channels will remain constant not only for first time slot, second time slot, but up till n time slot, all these channels remain the same. Yes, they are uncorrelated with respect to one another, but they remain the same up till the n time slot. So once you take it right, this means it's Hermitian. This whole vector will multiply with this, then this whole vector will multiply with the second column, third column, and up till the n column. So this, if this length is 1 cross L, and this length is L cross n, so multiplication will give you 1 cross n, as the output is 1 cross n. Noise and noise will be present in each of the outputs of Y. Achha, if I ask a question, Haji, let us say I ask from someone, Haji, someone is present. Achha, yes, Chaudhry Umair Ahmed, can you listen to my question? Chaudhry Umair, are you there? All right, good. You can turn on your mic.
Yes, sir.
All right, good. So if I ask you one question, keeping my notes open, is W Cn0 n0 or it is n0 n0 by 2? Meaning W is a complex Gaussian random variable, or it is just a real random variable, real Gaussian random variable. Do you understand?
Yes.
N0 n0, or it is Cn. C is for complex, remember? And what will be your answer?
A complex random variable.
Very good. Very good. This will be complex because the problem is that in general we can have space-time codes which could be complex. All right. So this means you have to receive a signal at both the channels. All right. But here, let us say if I use only BPSK, then you can say, oh no, it will be n0, but generally, yes, it will be on both this. All right, you can turn. You can mute your mic.
क्लैरिफिकेशन थोड़ी सी चाह रहा हूँ फिर मैं यहाँ पे।
Yes,
क्वेश्चन है
good, good.
सर, अगर अभी तो ये केस है ना कि अगर हमारे पास वो होंगे ऑर्थोगोनल चैनल वाले स्कीम्स, तो इसमें W जो होगा वो CN होगा। अगर हम ओनली BPSK करें या जो हमारे पास लीनियर वाले होते हैं पैम वगैरह में, तो इसमें ये n0 ही रहेगा, यानी कि रियल रहेगा, जिसके अंदर हमारा ऑर्थोगोनल चैनल नहीं आता।
Yes, I was saying in BPSK you are not utilizing. Similarly, in simple PAM, right, if
Exactly.
you use PAM, as you're not utilizing the Q channel, so you are right.
जी.
You will be just receiving only the single on the signal channel, because there is no use in getting the signal or doing all the analysis on the Q channel quadrature phase, because there will be no signal there. Yes, you are right. All right. Now, very good question that comes so let us say it is like this. All right. So I have just explained this equation. Now, what is the error probability? Question is, what is the error probability? Let us say I have two code words. Okay. Now, questions you say, sir, how I have two codes? Because I'm making this for students get confused. Questions, they normally come from space-time code in exam, and students, they get confused. Remember that for each different combination of BPSK, you will have many you will have different code words. All right. They can have, for example, here we saw, let us say, for LMOT, let us say, yes, this is the code word. Now, if I say, all right, sir, U1 is A and U2 is A, you can say, all right, then the code word will be AA minus AA. So you said, no, I form another code word. I say U1 is A, but U2 is minus A. In that way, this will be A minus, this will be plus A. And this will be A. So you have another code, because you could send 2 bits U1, U2. So you will have 4 different code words when you translate BPSK onto LMOT scheme. All right. One could be A minus A, other could be AA, other could be minus A, one could be A minus A, other could be minus A. And you have, in this way, you could have 4 code words. All right. So now 4 code words are there. And
Sir, एक question है.
Yes, you can ask, please ask.
Sir, जी सर, थोड़ी सी कंफ्यूजन ये है, इस जो आपने लास्ट अभी बात की है ना कि एलोमोटी के केस में 4 कोड वर्ड्स हो जाएंगे, वैसे बीपीएसके में 2 होते हैं, तो यूजुअली जो मॉड्यूलेशन होती है वो तो हमारे कम्युनिकेशन सिस्टम का लास्ट मॉड्यूल होता है, तो ये कोडिंग वगैरह पीछे डाटा की बेस पे हो रही है, तो इवेंचुअली जो कोड जा रहे होंगे आगे वो तो बीपीएसके के 2 ही सिंबल जा रहे होंगे ना, या 0 जा रहा होगा या 180 वाला जा रहा होगा?
अच्छा, नहीं, remember that yes, all right, you can mute yourself, I can answer. All right. Okay. Remember that LMOT schemes, these are diversity schemes. They are performed after they are after modulation schemes. They are just before the signal is to be sent onto the channel, because they have to introduce diversities. So you have done the digital communication part, you have applied BPSK or whatever. Now you have to send your symbols through these LMOT schemes or rotational or diversity scheme, convolution block code, and all these things, which have to fight or combat with the channel. So you can use that. All right, I can use my LMOT encoding before, and then I can send my modulation, or you could use your LMOT scheme afterwards. Okay? But in general, when we are modeling our systems, we use these schemes after modulation, because these schemes are working for channels. Okay. So but you can say that, all that I say they are working, I can do, for example, channel coding, so I can put them in terms after channel coding and then modulation scheme. This doesn't make much of a difference, but normally when we are trying to explain, we say, all right, you have done the digital communication part, then is now the part for applying diversity. So we first study time diversity, then we are studying space and time. Then we study space, and then we are now studying space and time. But it is, equal whether you apply it before or after. Doesn't make much of a difference. But from conceptual point of view, we normally say we apply this after, so that you are getting those symbols, and then you are adjusting those symbols intelligently across space and time. So you have those bits. Bits have been, let us say, converted to S1, S2 signals. Then now you are sending your signals, intelligently in space and time. So if I say that U1, U2, they are A and minus A. What is A and minus A? A and minus A, they are actually signals, actual signals. Okay? They are actually signals in the orthonormal basis. They are signals. So I am sending the signals intelligently like this in space. This is what is the L-Moty scheme or other schemes. So I am working after modulation to combat the channel. Okay. This answers the question.
Yes, sir. Fine. Thank you.
मैं क्या discuss कर रहा हूँ? All right. So you could see that where is the calculation? Oh, so we are sending. Let's say we have two. We send only two symbols, XB and XA. So what is the probability of error confusing XB and XA? So you could see here that this will be XA or XB. This could be H into XA or H into XB. Here which I show you. And this could be two symbols. Probability of error will be same thing. Confusing UA with U. But what is UA? UA is actually H into XA, but UB is equal to, this is the receive signal. But you can say receive signal is actually receive vector. Yes, this was a vector, this was a matrix, but when you multiply, I get 1 cross n, which is a vector. And I have just entered a vector in complex space. Vector in complex space, and we have just seen error in confusion between two vectors is actually this thing. So directly apply the formula. The formula that we have just discussed is derivation. Just apply the formula. So probability of confusing XA and XB, when we know that XA was transmitted and H is the channel, is just what? UA minus UB. Receive signal minus receive signal. This minus this. 2n0 by 2 under root n0 by n2. Now, what I can do, just to simplify, I can take under root, above here. This will become a square. This will become 4. So 4 and this 2 cancel with 4. This will become 2. All right. So n0, this is the total under root. So n0 will become n0. So 1 over n0 is my SNR. This will become SNR. And here you have this mod. This mod. This will become mod of square, because this comes inside the under root. Now how can I open my mod here? So I think this is more than enough. So how can I open my mod? This is mod square. So you can see the this will be actually H we know is n cross 1, but because of this is actually equal to 1 cross n. All right, this is 1 cross n, and this is actually XA minus XB. All right, so XA minus XB, which we just saw, was equal to L cross n. All right, and H size is actually L. So this is actually 1 cross L. All right, so you can see this was your H, but HH is actually 1 cross L, and this is actually L cross N. All right. So, and this total, when I multiply this, comes out to be 1 cross N. Okay. So how can I find its mod square? I can find its mod square when I will say, all right, this vector 1 cross N, and then multiply with its H n cross 1. So that when I multiply, n cancels, and I have 1 cross 1, I get a scalar value. So I can get the dot product, which will be actually the mod square of HHXA minus XB. So some students, they get confused because normally when we define mod square of a vector, we say WH into W, because in that case your W vector is actually n cross 1. In that case WH, so it becomes 1 cross n. But here, you know, this is already 1 cross n. So you will keep this first and the other second, so that when you multiply, you will get 1 cross 1. If, for example, you keep its conjugate here, then you will get n cross 1, and this will be 1 cross n, and then in that case you will get a n cross n matrix. Just an alternation that you have to work for the matrices is that. So opening this mod square, this will give you 1 cross n cross 1, so that you get 1 cross 1 or a scalar output or its mod square. Okay? It's mod square. So this comes out to be this thing. This comes out to be like this. I think I need to go further. So I think we have driven up to this part here. SNR, this is, you know, book uses H conjugate, but it's better that we use HH because H means transpose plus conjugation. If you compare this with the book, and you can see everything has been driven. H means conjugate, so we have done till this point. Now here is a very important result, and that is that this complete matrix, you can see it is actually Hermitian. Haji, anyone remembers what is Hermitian? Hermitian means
It's conjugate
that
transpose.
if you take its Hermitian, it will be the same matrix. Hermitian of this will be same, because you take its conjugate, this goes here, this goes here, this becomes H, which is this, and this becomes HH, cancels HH and becomes this. So this is Hermitian. So you know, transfer this is the same thing. This means this is Hermitian matrix. So once one thing is Hermitian, you know, it is can be diagonalizable by unitary transform, or you can take its eigen eigen analysis. So I can write this as eigen matrix, eigenvalues, eigenmatrix, and eigen matrix. It will contains all the eigenvectors q1 to up till qn, all the columns, n columns, it will be there, q1 to qn. Un is a unitary matrix, a diagonal matrix. Here are the singular values of difference matrix. Because you know there are two matrices xa minus xb into xa minus xb conjugate, so that is why he is writing them as square. So that lambda is for 1 because the square is there, that is why he is saying they are for single. So how I can write the error probability? Again, he has missed a lot of steps here, so I will try to make you understand how you can come up with these steps. So we have driven up to this point. So I write xa minus xb as eigen decomposition as follows. We remember here that what is H? H is a vector. What is U? U is a matrix. All right. Where actually this totally actually represents xa minus xb. xa minus xb. So if you see xa minus xb, what was this thing? So you could see this was of size L cross N, and this will be N cross L. So total this was a L cross L matrix. So if I will write its transformation or its eigen decomposition, I will get L cross L orthogonal matrix, eigen matrix, L cross L orthogonal matrix, Hermitian. So like this, because you know once you decompose it, it just sees the total matrix, which is L cross L. Now let us do the multiplication here. Remember, H is actually H1 to HL. So conjugate this means 1 cross L. So if I multiply this with U, now what is U? U is actually a matrix which contains U1, U2, U3 up till UL, and all U1, U2, and they are all orthonormal, or you can orthogonal columns or orthonormal columns. Okay. So once I will multiply, so H will become like a vector 1 cross L. So here this will be a column with Q1. So H will go with Q1. Correct. H conjugate will go with Q. Then H conjugate will go with Q2. Then H conjugate, and the size will be LL 1 cross L. So you have 1 cross L vector where whole vector is going with all of those Q's present in the orthogonal matrix. You can also orthonormal matrix. Oh, sorry. So he has missed a lot of stuff. Let us go back to this mathematics. Now again, you can do the same thing here. Okay. And you can see this is again L cross L. This is L cross 1. So once you multiply, you will get actually L cross 1. So each of those Q's, Q1 will go with whole H, Q2 will hold H, and all of those Q's will be conjugated, or Hermitian transpose. So Hermitian, this eigenvalue is present is still in between. This is L cross L. Then you can see that I do the second step. I do their multiplication. So 1 cross L, L cross L. This will give me 1 cross L. This will give me 1 cross L. And what will be that 1 cross L? This will be H1 Q1 into this column. This will be lambda 1 0 0. So just gives me lambda 1. Whole vector with lambda 1. Second will go whole vector with lambda 2. Lambda 2, and so on and so forth. Whole vector with lambda L, because they are all squares, because we have put them as lambda squares. So again, you have a vector whose size is 1 cross L, where each value is dot product of H with Q1 into lambda 1, lambda 2, like this and like that. So I get here. This is already there, which is L cross 1, 1 cross L. So I multiply, I will get a 1 cross 1 scalar value. This will all go with this. So HQ1 lambda 1 will go with Q1. So you have H conjugate H and Q1 with Q1 conjugate. So you can write this at H Q1 Q1, or you can write as L goes from 1 to L. H with H, H conjugate with H, Q L conjugate with QL with QL conjugate, because it's not conjugated here, it is conjugated, and lambda 1 square, and summing them up all. They are all summing up them. So this is actually a dot product. So I can write this as, because this is the complex conjugate of this thing, so I can write this as H conjugate QL mod square, like this. All right, this is a scalar. Sum of all these scalars, or I can rewrite this as QL cross H. All right, this won't make any difference. Right, so QL cross H, and I can say that this is equal to some term, because again this is a scalar. L cross L, this is a scalar square into lambda square, and so these are lambda squares. All right, so each one of them will multiply their lambdas, these values, sum them up, you will get a value. So this is sum of these HL squares. So he has just written that sum of these HL squares, where this H delta is U conjugate H. So yes, where there's actually, you can also write this as U conjugate H. So actually same thing here because we got this, but you can also write this as Q conjugate H, because they will give you the same result. Dot product with this or dot product of this with this. Results are the same here. So I can write this as follows. Q conjugate with H. This gives me H1, H2, HL. So, sorry, this gives me this HL mod square with lambda L. So this is error in confusing A with AB can be written as follows. Okay. Now you can see here that what is HL? HL is again a Rayleigh channel, because you know HL is actually you know in Rayleigh we had you know noise, both the real complex Gaussian random variable, both the real and random variable, then it becomes a Rayleigh complex Gaussian random variable. Rayleigh has both the noises, you know, in the I and Q channel, it becomes a Rayleigh channel. And so H del is, which is actually U into H, is also Rayleigh, because U is again, you know, it is orthonormal transformation. Okay, orthonormal vectors. Once ever you multiply orthonormal vector with any Gaussian vector complex, it remains the same. All right. So this will also be CN01, and hence this will also be Rayleigh, and hence all these H mod squares, they are also Rayleigh. So we have done for Rayleigh, no problem. We have just done when we were studying rotational codes. So we have seen in the case of rotational codes, so we have seen when we were doing the mathematics that in case of rotational codes where H1 mod square and H1 they were Rayleigh, you could very well write your error to be less than you know SNR times whatever the term here, and then you can approximate for Rayleigh as 1 over SNR d1 square over 4. Okay, where actually square 2, but it comes out to be 4 because then you have this 2 here. So whatever the thing with the H1 mod square SNR d1 2 divided by 2 4, it finally comes here 1 over d4 for Rayleigh there, as we have seen. So we can repeat that same procedure for this Rayleigh channel, and repeating the same. So with any tilde, what is the SNR lambda L2? So I can just write 1 plus SNR lambda 2 over 4 as you have done previously, no problem. And all of these are being multiplied as they were being multiplied before for rotation. We have seen all of that. So we got this thing. Here you can also see that because this is multiplication, again we have done this. So we say the SNR is large, so we can neglect this one, or you can say this is upper bounded by this factor. So we can neglect one, or we can say, all right, no, don't neglect one, but this is less than this thing, so it is upper bounded, or you know, so a multiplication of these things, but 4 and SNR, they are constant, they come out, but L times will be L. So this product will be just product of these eigenvectors or the eigenvalues. And very, very important proof in linear algebra is that the product of eigenvalues is what? It is actually equal to the determinant of the actual matrix. So the product of the eigenvalues of a matrix is equal to the determinant. So the proof is available in that in any linear algebra good book. You can see there. So now we have a very, very important result. The probability of confusing yes, sorry. So we have a very, very important result here, that probability of confusion is actually nothing but the determinant, but the determinant of your code word, you know, the difference of the code words Yes, we are finishing. Difference of the code words between XA and XB. All right. So we will find the difference. For example, for we say BPSK over LMOT scheme, we saw that we have 4 code words. So I will find the difference between 1 and 2, find the difference between 1 and 3, find the difference between 1 and 4, find the difference between 2 and 3, find the difference between 2 code and 4 code. Similarly, find the difference between third code and 4 code. All the coded differences I will find. Okay. And then I will see what is the minimum distance. So the coding gain will be driven by the minimum of the determinant over all code words. All right. So you can see that this is a diversity gain. While what is this? This is the coding gain, as we have seen in notational codes. So anything which comes with this thing, it is actually the coding gain. All right. I hope you have understood. I will end the lecture at this point. So if you have any questions, you can ask. So then we will move on to attendance. Haji, if anyone has any questions, then you can ask. Rest of this is application of this criteria to various schemes. There are also many schemes are given, and then problems also. Some we will discuss here. I will try to also present, some examples so that we are well versed in finding the probability of error based on the space-time criteria. If you have any questions, you can ask now. All right, so no one has. Yes, please ask.
Sir, today we discussed, sir, it is better to give an example of these codes, sir, to explain these concepts.
Yes. My procedures are first we will cover the book. First we should cover the basic concepts, the mathematics, the required concepts concepts which are required to understand. All right. Then we can do some examples. So we will discuss an example in the next lecture because the time is up. But derivation is also very, very important, or getting the concept of all these orthonormal bases, orthonormalization, channels, noises, their vector representation, matrix representation. So you need to build up this type of mathematics, linear algebra for these future wireless systems. Then we will see the example in the next lecture, so we can compare different space-time codes, or let us say a single space-time code but with different schemes with PAM or QPSK or all that. So we will be discussing, no problem. Any other question? So I think no one has any question. So I will move on to so there are 10 attendees. So I will also download them, try to. So actually you could see that this type of knowledge is not given in an undergrad wireless course. There I have just was seeing one university that was making wireless course, the paper. So they mainly base it on the system requirements, not on these diversity and coding, which are actually very important in understanding at a higher level of these 4Gs, 3Gs, 4Gs, and then finally going to 5 and 6Gs. So I will share the screen now for attendance. So I think you can all see the attendance in front of you. Already I'm taking the attendance. So this is 19.5 PhD.
Present.
1835.
Present.
Good. 1836. All right. Present. Good, mashallah. 1837. Uh, 7 is present.
Yes, sir. I'm present.
All right. 39.
Yes, sir.
42.
Present, sir.
All right. 62. All right. 63. 41.
Present.
42.
Present.
All right. 43. All other students, please turn off your mic. 43 is present.
Yes, sir.
Good. 46.
Yes, sir. Present.
So 10 are present and 10 have been marked. Very good. So attendance is safe. Achha, one thing I just forgot to actually discuss. I have I was trying to update. You can see here. If I just share the screen. So I have I have uploaded some of the lectures, so you can get those lectures here. I'm also trying to upload other lectures, in this file folder. So you have the recorded version of all of them. Well, it takes a lot of time. Anytime you have these. So this is there, but I will be inshallah putting all the lectures here, so you won't have any problem. So you will have the lectures. You can download from here. Actually, another thing that I wanted to show is that I have updated the outline, and so this has a time, because some things they will be plus and 1 and -1. So here I was so you could see here that I've updated this. I will also update here, because as we have discussed some other things also which were not present in the original. So I don't think it will be covered in the next week. I think it will take another lecture. So let us say 12th week. So we will have another quiz or assignment, but we need to cover. We have covered approximately space and code is almost covered, but we need to cover this MIMO thing in the next lecture onwards. So it might take a week or 1.5 of a week. So whatever. So then we will have a quiz. So I will be searching for how could we conduct a quiz. There are various ways. You can also give me certain ideas of conducting the quiz. So it will be a short form. You will be given a small amount of time, and in that time you have to do some calculations, or you can send those screenshots, and there will be a folder where you can upload it. This could be like this, or in other words, you could have so choose the best answer, so that whatever something will be asked. But again, if there is some problem in this, I have to discuss with other teachers. Then in that case, you might be given an assignment. But whatever, we will have this.
सर आप असाइनमेंट ही दे दें.
At this point, I cannot say for sure, because both options are there in this MS Teams. So, but I will be discussing with other teachers. Then I will tell you. But it will be either after the 11th week or after the 12th week, depending whenever we complete this MIMO thing. Right? There's just beforehand information I was giving. Let's also update this thing to mention whatever we have covered here. Right? forgot. So I will end the lecture here. All right. So if we will be discussing other things in the next lecture. All right. Thank you.